Hello and welcome to a lesson on the unit circle. We'll be looking at a method that we can use to compute the sine and the cosine values for angles that are not just limited to being acute. So if we have, say, a 30, 45, or 60 degree angle, those are acute angles, but we can then apply this idea of a unit circle and rotation and sort of symmetry to compute the sine and cosine for values that are more than 90 degrees. And then we'll also look at a fundamental identity at the very end. So the idea of a unit circle is it's a circle. It's centered at the origin and it's a radius of 1. So its radius is 1 unit, hence the name unit circle. And so again, if we remember what we talked about before is rotation can be either counterclockwise. So counterclockwise is positive rotation, or clockwise would be negative rotation, and it's unlimited. So we're not just restricted to having rotation within the first quadrant. We can rotate as much as we want. It's unlimited. And so that's kind of what we're wanting to get, is we want to expand from just acute angles in the first quadrant to being able to go anywhere around the circle. So to do that, let's just kind of zero in on the first quadrant and just kind of look at some angles, some special values that we can come up with. So in a previous lesson, we looked at the 45-45 right, 45-45 90 triangle. And so if we were to take that triangle and sort of insert it within the unit circle, so one vertex, one angle is at the origin, and the other is located out here on the circle. So again, it's that hypotenuse of that triangle is a radius of 1. And then since it's a 45-45 90, we know that if the hypotenuse is 1, that both of the legs are square root of 2 over 2. So if we were to look at the point on the circle, its x and y coordinate would be the same as the horizontal width of the triangle versus the vertical height of the triangle. So that means the x coordinate for this point on the circle is root 2 over 2, and the y coordinate is also root 2 over 2. Okay, so at a 45 degree angle, the point on the circle has the x and y coordinates of root 2 over 2. So we can do the same thing with our 30 and 60 degree angles. So if we look at a 30 degree angle, we know that the opposite side is a half, the adjacent side is root 3 over 2, and that's all when the hypotenuse is 1. So again, x and y, x is the horizontal distance, y is the vertical distance. So the point on the circle has an x coordinate of root 3 over 2 and a y coordinate of 1/2. And then if we repeat this again for the 60 degree angle, again, if the hypotenuse is 1, the side opposite the 60 degrees is square root of 3 over 2. This adjacent side is 1/2. So again, the 1/2 is the x coordinate, the x dimension. The root 3 over 2 is the y coordinate. So that means for our coordinate here on the circle, the point on the circle, its coordinates would be 1/2 comma root 3 over 2. Okay. So if we put all three of those together, we get rid of the triangles and we just think of those as angles. At a 30 degree angle, the point on the circle is root 3 over 2 and a half. At 45, both x and y are root 2 over 2. And then at 60 degrees, we get 1/2 for the x and root 3 over 2 for the y. And there's a couple others that we can look at. We don't really have triangles for these, but if you were to locate the coordinates for the point on the x-axis that's on the circle, where the circle and the x-axis intercept, it will intercept at the coordinate 1, 0. So that gives us a way to figure out, hopefully we'll see a sine and cosine if you have a 0 degree angle. And if we look at the top of the circle where the circle intersects the y-axis, again, that would be at a 90 degree angle, we get the point 0, 1. Okay, so those are kind of the special points that we have in the first quadrant. Those are, and it's just based off of the two triangles that we had for acute angles. So now what we're wanting to do is connect that graph, that first quadrant, to our sines, cosines, and even tangents eventually. So to do that, remember, if we look at a right triangle where the hypotenuse is next to our angle, it's opposite the right angle, and then our angle here is near centered at the origin. From the angle, we have an opposite and an adjacent side. So it looks like this adjacent side is connected to the x-coordinate, and the opposite is connected to the y-coordinate. However, in a general sense, the hypotenuse can be any number we want. So in order for it to be a unit circle, I need the hypotenuse to be 1. And so if I were to take all 3 sides and basically scale this triangle, kind of like the scale on a map, if I were to divide all 3 sides by the hypotenuse, hypotenuse divided by the length of a hypotenuse would be a 1. Okay? And so if we divide the opposite divided by the hypotenuse and the adjacent divided by the hypotenuse, that sort of scales our triangle so that it fits within the unit circle. Okay? And this should look familiar. The adjacent over the hypotenuse, what is that? That's cosine. And the opposite over hypotenuse is sine. And so this gives us a really special relationship. When we look at the triangle inside this unit circle, the x-coordinate represents the cosine of the angle, and the y-coordinate represents the sine of the angle. And even using our other trig functions, our ratios, that tells me that the tangent of the angle will equal y over x. And we'll see that more in the next unit. But for now, we really want to pay attention to the fact that cosine is the x-coordinate and sine is the y-coordinate. All right, so we're trying to compute the sine of 30 degrees, which we've already seen this. We should, if we can remember it, we should know what it is. But let's use our unit circle. So here's the 30 degrees, and we know that sine is the y-coordinate. So the sine value has to be the half. So we know the sine of 30 degrees has to be a half. We go to cosine of 45 degrees. So for 45 degrees, find the 45 degrees on the circle. Cosine, remember, is the x-coordinate, so which it doesn't matter, it's the same x and y, but here it's going to be the x-coordinate. So we know that the cosine of 45 degrees is the square root of 2 over 2. Then we can look at the cosine of 30 degrees. So let's go back to our 30-degree angle. Remember, cosine is the x-coordinate, so cosine of 30 degrees is going to equal root 3 over 2. And then just as a last example here, the sine of 60 degrees. So let's find our 60-degree angle. And looking at the sine of 60 degrees, sine, remember, is the y-coordinate. So we're going to take this root 3 over 2. So the sine of 60 degrees is going to be a square root of 3 over 2. And again, that should match what we've seen in previous videos and previous examples without using the unit circle. So in general, say we have any point on the unit circle. It doesn't have to be in a point in the first quadrant. It can be any point on the unit circle. And with that point, we have an angle that's in standard positions. Remember, it starts at the positive x-axis and can rotate either counterclockwise or clockwise. And it's rotating about the origin. So if we have this point rotating around the unit circle, then for that coordinate, we know, again, we've already stated this, but the y-coordinate represents the sine of the angle, and the x-coordinate represents the cosine of the angle. And again, up to this point, we've only talked about what if we have acute angles. So acute angles have to be in the first quadrant between 0 and 90 degrees. And the whole reason we're talking about this is how do we expand our sine, cosines, and tangents beyond just acute angles? How do we get outside of this first quadrant? How do we get to, what's the sine of 120 degrees, for example? How do we get beyond just the first quadrant? And there's 4 things we're going to look at. We're going to talk about quadrantal angles. We're going to talk about the sines of the quadrants. We're going to talk about reference angles. And then just kind of a method I like to use for figuring out where is the actual angle located, particularly when you're talking about it in terms of radians, because it can be a little confusing. It's a lot of fractions and stuff. So let's first look at quadrantal angles. We say that an angle is quadrantal if it is coterminal with a coordinate axis. And I believe we've already stated this before. So some angles, the problem with this is that some angles may have undefined trig values if either the x or the y coordinate is 0. We're not going to see that right now, but we will see this once we get into our other trig functions. Okay, but so 90, 180, 270, 360, 570. So if we keep going around the circle to angles that are coterminal with a quadrantal angle, we will end up getting, we call those quadrantal angles. So let's look at this, a few examples here. The sine of 90 degrees. So if we wanted to look at 90 degrees, remember, if we thought of our unit circle here, 90 degrees is right here on the y-axis. So what is the coordinate? So again, this is a unit circle, which remember the radius, it's radius of 1. What is the coordinate up here? The coordinate is 0, 1. So remember, when we're talking sine, we want to deal with the y value. So the sine of 90 degrees, which is the y-axis, sine of 90 degrees is going to be a 1. All right, what if we wanted to do cosine of 180? Well, 180 is halfway around the circle. So 180, if we rotate it around, would be right on the x-axis, but it's on the negative x-axis. So what's the coordinate there? That coordinate is -1, it's 1 unit to the left, and 0 because it's on the y-axis. So the cosine is the x value, so cosine of 180 is going to be a -1. And just one more, cosine of 270. So 270 degrees, that's 3 times 90. So we're going to go 90, 180, and 270. So there's our 270 degree. The coordinate there is going to be 0 and -1. So cosine, remember cosine is the x coordinate. So in this case, cosine is going to be 0, which is totally defined. It's fine to have a cosine of 0. It's fine to have sine and cosines negatives. It deals with where's the x and the y coordinate, and that's it. Again, sometimes once we get like into tangent and cotangent and secant and cosecant, we will see some of these be undefined. All right, the next thing we need to look at is the quadrant signs. And so this will help us keep track of whether or not our sine or cosine values are going to be positive or negative. So all trig values are positive in the first quadrant. So sine, cosine, all 6 of them, all of them are positive in the first quadrant. Sine is positive in the second quadrant. Tangent is positive in the third quadrant, and cosine is positive in the fourth quadrant. Okay, so visually we might look at a graph. So we know all of the trig functions are positive in the first quadrant. Sine is positive in the second quadrant. Tangent's positive in the third, and cosine is positive in the fourth. If you look at the letters A, S, T, C, sometimes you may hear the phrase all students take calculus, and just to kind of remember that order, but that's up to you. So why is this the case? Why are these positive and negative where they're at? So, and it comes down to what do the sine and cosine represent. Remember, sine and cosine, sine is the y coordinate, cosine is the x coordinate. So since sine is y, sine is going to be positive. The y values are positive in the first and the second quadrant. Cosine is the x values, and x's are positive in the first and the fourth quadrant. So both of them are positive in the first, sine is positive in the second, and cosine is positive in the fourth, which means down here, sine is negative in the fourth quadrant. Tangent's a little different because it has to deal with both y and x. But again, if both of them are positive, tangent's positive. If one is positive, so if the y coordinate is positive but x is negative, you're going to have a negative tangent, so that's why it's not positive in the second quadrant. Third quadrant, tangent is actually positive. And that's because in the third quadrant, both the x and the y coordinate turn out to be negative. And so we just said a minute ago, tangent is y over x, and if you divide two negatives, you end up getting a positive. and then in the fourth quadrant it flips compared to the second quadrant. So it all comes down to whether the x coordinate or the y coordinate is positive or negative. Let's just look at maybe a couple examples here. We want to figure out the quadrant of the terminal side of an angle if we know the tangent of that angle is negative and the sine is positive. Okay, so if we think back to our little graph here, we know all students take calculus, right? So where is tangent positive? Let's first think about that. Tangent is positive in the first and the third quadrant. So where does it have to be negative? It has to be negative in the second and in the fourth. Okay, so that's tangent. So we know tangent has to be negative, which means we're dealing with an angle somewhere in the second or in the fourth quadrant. We're also told that sine has to be positive. Well, sine is positive in the first and in the second quadrant. So which of these, and then it would be negative in the third and the fourth. So which of these quadrants satisfies both conditions? Tangent has to be negative, sine has to be positive. Well, that would be right here in the second quadrant. So what quadrant is it? We know that it has to be in quadrant 2. Okay. Now let's take a look at another example. Say we're given that sine of theta is equal to a negative 11/12, and we know theta is in the third quadrant. We want to be able to figure out the sine values, the exact values of our other trig functions. Okay, so to do this, let's go ahead and draw a picture here. So we're going to draw our x and y axes, and we know we have some angle. I don't know what angle it is, but I know it's down here in the third quadrant. Okay, so theta comes around this way. Now I know sine is a negative 11/12. Okay, so remember sine is the opposite over the hypotenuse. So if I were to, just like we saw a few minutes ago, if we thought of this as a right triangle, you always draw the right triangle, the angle always is at the x-axis here. So the sine of this angle means this has to be the opposite and this has to be the hypotenuse. Now remember, sine is a y-coordinate, so if this y-coordinate is below the x-axis, what's it mean? It means it's actually a negative 11. Okay, so we know this left side has a negative 11 and then the hypotenuse is a 12. In order to figure out the other trig values, we're going to need the adjacent side. So let's just call that x for now. So we know x squared plus a negative 11 squared has to equal 12 squared. If we go ahead and we solve this for x, we're going to get x squared is equal to 23. So x is going to be the square root of 23. So that means this side, again, is the square root of 23. But again, it represents an x-coordinate as well. And since that's going to the left of the y-axis, I know this has to be negative. Okay. All right, so let's compute our sine, our trig values. So we already know the sine of theta is a negative 11/12. To find cosine of theta, cosine is the adjacent side, so that would be the negative square root of 23 over 12 over the hypotenuse. And then tangent would equal the opposite, negative 11, over the adjacent, which is a negative root 23. And again, since we have a double negative, this turns out to be a positive 11 over root 23. And I'm not going to do it now, but we could go ahead and compute the cosecant, secant, and cotangent, just like we did in the previous lesson. All right, one more example. So what if we know the cosine of an angle is 4/5, and we know that the sine is negative? Can we find the sine of angle theta? Well, cosine is 4/5. So again, go back to our our angles. We know it's all students take calculus. So cosine is positive in the first and in the fourth quadrant. So wherever theta is, it has to be in the first quadrant. We're also told it is negative. So sine is positive in the first and negative in the fourth. So our angle has to be in the fourth quadrant. Okay, so we know we're rotating around here somewhere. I don't know how much. And I have this angle in the fourth quadrant. Now, again, if we do kind of a similar thing, we could think of this as a right triangle. Because it's cosine, I know the adjacent side is 4 and the hypotenuse is 5. So we need to figure out the sine value. So for sine, we're going to need the y-coordinate. Again, we're going to do Pythagorean theorem. So we're trying to find y. So 4 squared plus y squared must equal 5 squared. So if we go ahead and we solve this, we solve it for y, we'll get y squared is equal to 9, which y then turns out to be, technically it could be plus or minus 3. When you take the square root, you get plus or minus. Well, which is it? Well, again, we're talking a y-coordinate, and it's below the x-axis, so this actually turns out to be a negative 3. So if we wanted to compute the sine of that angle, we know sine is the opposite, which is the y-coordinate, over the adjacent, or over the hypotenuse. So the sine would be a negative 3/5. All right, next we need to look at reference angles. Again, our whole point here is trying to talk about how can we go beyond acute angles. So the quadrantal angles give us a way to talk about the 90, the 180, the 270 degrees. Reference angles are going to, again, give us another way to tie the angles in the second, third, and fourth quadrants back to the angles in the first quadrant. So first we need to define what a reference angle is. So a reference angle, it's an acute angle. It's always an acute angle, and it's always positive. It is formed between the terminal side of your given angle and the x-axis. Okay, both your original angle and your reference angle will have the same trig values. So they'll both be a half, or they'll both be √3/2. The only difference is they may have different signs. So one may be a positive half, the other may be a negative half. And that's where the quadrants that we just talked about comes into play. Again, so if you were given angle theta, which this is standard position, is rotating from the x-axis into the second quadrant. So this is an obtuse angle, but the reference angle is from the terminal side down to the x-axis. And this reference angle is now an acute angle, and we're just going to think of it as a positive acute angle. And positive acute angles we can then talk about as values in the first quadrant. All right, so let me sort of try and illustrate this a little bit more. So say we had an acute triangle in an acute right triangle in the first quadrant, okay, and we're having some angle of rotation. Angle theta rotates from the x-axis up to some point in the first quadrant. Okay, this is an acute angle. Well, there is an angle in the second quadrant. So we're rotating past 90 degrees, so we're going to have an obtuse angle. But if you remember, in order to rotate around to 180 degrees, this obtuse angle is going to have an acute angle with it to get to 180. And so this acute angle could be equal to this acute angle in the first quadrant. Okay, so angle B here is an obtuse angle, but its reference angle below is actually an acute angle, and this acute angle is the same as that acute angle. And we could draw another example in the third quadrant. So we now have this reflected angle. It's more than 180 degrees, but I could still sort of relate it to this acute angle, and it turns out that I can find an acute angle in the first quadrant that's exactly the same. And similarly, in the fourth quadrant, we could have an angle that goes all the way around past 270 degrees, but it still has this small acute angle that's associated with it, and that acute angle is inside the right triangle. Okay, so looking at them all together, we can find any angle that I rotate around to, and it doesn't matter whether you're rotating once or twice or 100 or in the clockwise direction, any angle always has an acute angle that's related to it. And that acute angle has to be the same as an acute angle in the first quadrant. Okay? So again, this is kind of a weird idea to grasp, but hopefully it'll make some sense. So if we had a 300-degree angle, okay, so with 300 degrees, so if we rotate 300 degrees, there's 90, 180, 270, and then 300. Okay, so if this whole angle here is 300 degrees, what is the angle inside here? So how far is it from 300 to 360? Well, that means this angle in here is 60 degrees. So 60 degrees is the reference angle for the 300. What about a negative 135? Okay, so it's negative. That means we're going to rotate in the clockwise direction. So we're going to rotate to negative 90, and then we're going to stop. If I kept going, I'm going to hit up negative 180, so we don't want to go that far. So here's a negative 135 degrees. Well, that's an obtuse angle. It's negative, but it's an obtuse angle. How far would I have to continue rotating to get to the x-axis? Well, I'd have to rotate an additional 45 degrees. So this is my acute reference angle, just like the 60 was my acute reference angle. One more maybe. So say we had 510 degrees. This one's going to be a little harder, but so we start rotating, we hit 90, 180, 270. We got to keep going. 360. 360, what comes after 360? 360 plus 90 would be 450. 450 plus another 90 would be 540. So we're going to stop here. So this is a 540 degree angle. Okay, it's a 1.5 revolution. Well, what's the acute angle there? Now this one's kind of a weird one. We actually don't have an acute angle with this one. But what is this angle related to? What would be coterminal to this? So this doesn't necessarily have a reference angle, but I do know that this would be the same thing as 180 degrees. So we can, if we don't have an acute reference angle, we can at least have a coterminal. In fact, this is coterminal. We could also call it a quadrantal. Okay, and so quadrantals are a little different, but again, we need to be able to talk about any rotation, any amount of rotation around the circle. All right, so the last thing we just want to look at real quick is angle location, and this is, again, particularly going to focus on radians. It's easy to, counting through the 360 degrees is pretty easy. So how do we deal with this if we are in radians? So in radians, again, this is 0 degrees is the x-axis. It's also 0 radians. And we talked about earlier, if you rotate halfway around the circle, you get pi radians, which means all the way around to the circle, you get back to 2 pi. Okay, so how much is half of pi? Okay, or in other words, how much is half of the half circle? So half of the half circle would put you right here. So the y-axis, the positive y-axis, is a rotation of pi over 2. Okay, this would be pi. So what would be between pi and 2 pi? Well, it turns out that this one is 3 pi over 2. Okay, so rotating 90 degrees is pi over 2. Rotating 270 degrees is 3 pi over 2. And there's sort of a strategy I like to use, is think and count in common denominators. So this is 0 pi over 2. This is 1 pi over 2. So pi, if you wrote it with a common denominator, would be 2 pi over 2. And then we get down to 3 pi over 2, and then we get back to 2 pi. Well, 2 pi is really 4 pi over 2. And I could keep going. So this would be 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2, and we could keep going, and just you could count forever. You could also go in the negative direction. So if this is 0 is the x-axis, negative pi over 2, so negative 1 pi over 2, negative 2 pi over 2, negative 3 pi over 2, and we could keep going. Okay, so just if you count in terms of a common denominator, count by fractions, hopefully it's a little easier to figure out where your angles are. It's, the more of this you get the hang of it, the better you'll understand it. So if we want to count by pi's over 3, so remember pi over 3 is 60 degrees. That means you're taking half of the circle, because we're taking pi, and we're dividing into thirds. So that means you're going to have 1, 2, 3 sections, and then you're going to have another 1, 2, 3 sections in the bottom of those sectors. So if we do sort of the same thing, here's 0 pi over 3, this is 1 pi over 3, and then 2 pi over 3, and then this is 3 pi over 3, but what's 3? That's 3 pi over 3 is really just pi. We keep going though. You have 4 pi over 3, and then 5 pi over 3, and then you get to 6 pi over 3, but 6 pi over 3 is really just 2 pi. We do the same thing with pi over 4, which is 45 degrees. So that means you're taking pi, so from 0 to pi, and you're dividing into 4 parts. So you're going to have 4 sectors on the top and 4 sectors on the bottom. So 1 pi over 4, 2 pi over 4. Well, that's actually just the same thing as pi over 2. You then get 3 pi over 4, and then this would be 4 pi over 4, and then 5 pi over 4, and 6 pi over 4, and 7 pi over 4, and 8 pi over 4, which is again 2 pi. So again, we could count around. And then one more, we could do this with pi's over 6. Pi over 6 is 30 degrees. So again, you're going to have 1 pi over 6, 2 pi over 6, which turns out to be the same thing as pi over 3. And then you could have 3 pi over 6, which turns out to be pi over 2. And then you could have 4 pi over 6, which is 2 pi over 3. You could have 5 pi over 6, and then 6 pi over 6, which is really just pi. And 7, 8, 9, 10, 11, and then you get all the way back to 12 pi over 6, which is just 2 pi. So again, we can count, we can keep counting as many as far as we need to go. And we could, I kind of included one to show you what pi over 12 would be. That's going by 15 degrees. The nice thing with this is it hits all the pi's over 3, all the pi's over 6, pi's over 4, and the pi's over 2. So it hits all the ones we've talked about already. But again, you just count around. 1 pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12, and onwards. Okay. So hopefully that'll kind of help you figure out, particularly when you're dealing with radians, where a specific angle is located. All right, so how do we go about computing our trig values for any of these special angles? Okay, so the first thing we want to do, and you'll kind of get the hang of doing this, but for now we want to draw the angle in standard position. So starting from the positive x-axis and rotating around the origin, and you may need to do sort of some sort of counting technique to get all the way around it. Then we need to figure out what is the reference angle. So, or is it a quadrantal angle? Okay, so what is that acute angle? Once we know the acute angle or the quadrantal angle, we can figure out what is the trig value for that reference angle. Okay, and we're almost home at this point. Last thing we really need to do is figure out, is that value, whatever answer we got for step 3, is it going to be positive or negative? And again, that goes back to all students take calculus. Which quadrant are we talking about? Okay. Once we get all that stuff figured out, we just write our answer and we're done. Okay. So let's work through a few examples here. So say we wanted to do the cosine of 5 pi over 6. All right, so 5 pi over 6, again, if we wanted to count, we have, here's 0. We would then have 1 pi over 6, 2 pi over 6, 3 pi over 6, 4, and 5. So it's over here in the second quadrant. So we're rotating all the way around to here. That's 5 pi over 6. Okay. Well, if that's 5 pi over 6, what is our reference angle? Okay, my reference angle has to be, I don't want to do that. So what is our reference angle? Our reference angle would be pi over 6. Okay, it's going to be the same denominator, you just get rid of the 5. Okay, so think about what is the cosine of pi over 6. Well, pi over the 6 was 30 degrees, and I know cosine is the x coordinate, so my answer has to be a root 3 over 2. Okay, because I know 5 pi over 6 has a reference angle of pi over 6. Again, it's going to be the same denominator, just drop the 5. And we know the cosine of pi over 6, which is the cosine of 30 degrees, is root 3 over 2. Last thing we got to figure out is what is the sine. So the sine, is it positive or negative? Since it is in the second quadrant, we know cosine is negative in the second quadrant. So the answer, so if we computed cosine of 5 pi over 6, we will end up with a negative root 3 over 2. What if we wanted to try another one? So let's look at sine of 5 pi over 4. So again, let's first draw it. So if we're doing pi's over 4, we got 1 pi over 4, 2 pi's over 4, 3. 4 pi over 4 is the x-axis, and so that means we're down here. So here's 5 pi over 4. Okay. So what is the acute angle from the x-axis to our terminal side? Well, if that's 5 pi over 4, our terminal angle, our reference angle has to be pi over 4. So let's compute what is the sine of pi over 4. Well, go to our little first quadrant here. We know pi over 4 is 45 degrees. And at the y-coordinate, since we're talking about sine, the y-coordinate is root 2 over 2. So we know our answer is going to have a root 2 over 2 in it. We just need to figure out, is it positive or negative? Well, all students take calculus, so the third quadrant only tangent's positive, so that means sine has to be negative. Okay, so we know the sine of 5 pi over 4 is a negative root 2 over 2. All right, the last one, sine of pi over 2. Okay, we want to draw our axes again, draw our angle in standard position. Pi over 2 is 90 degrees, so we're just going to rotate to the y-axis. Okay, so at 90 degrees, this does not actually have a reference angle. Okay, this one is a quadrantal angle. So instead of a reference angle, we want to just look at the point on the unit circle. So what is the coordinate on the y-axis? It was 0, 1. And we want to deal with the y-coordinate. So the sine of pi over 2 is 1. All right, let's do a few more examples. Cosine of 7 pi over 6. So we got to count by pi's over 6. So we're going to take pi and divide it into 6 parts, just in the top. So 1, 2, 3, 4, 5. So that gives me 6 parts on top, and we need to go one more. So we're going to go down here. So that's 6 pi over 6, which makes this 7 pi over 6, 8, 9, 10, 11, 12 pi over 6. So we are rotating all the way around to here. So if this is 6 pi over 6 and this is 7 pi over 6, what's my reference angle? My reference angle has to be pi over 6. Same denominator, just get rid of the 7. And so we want to think about what is the cosine of pi over 6. Well, Pi over 6 again is 30 degrees. We know the cosine of 30 degrees is root 3 over 2. So I know this has to be root 3 over 2. So I know this has to be root 3 over 2. Is it positive or negative? So what do we know about cosine in the third quadrant? Only tangent's positive, so that means cosine has to be negative. All right, sine of a negative. Ooh, we got a negative this time. Same thing, we're just going to rotate in the other direction. So we're taking pi, is actually a negative pi. So from 0 to negative pi, and we're going to divide it into 4 parts. So this is negative pi over 4. This is negative 2 pi over 4, which makes this here a negative 3 pi over 4. So we're rotating this direction. Okay, so what is the reference angle? If that's negative 3 and we're trying to get to negative 4 pi over 4, that means my reference angle is pi over 4. So what is the sine of pi over 4? The sine of pi over 4, sine is the y coordinate, it has to be a root 2 over 2. All right, go back. The last step we look at is what is it positive or negative based on the quadrant. Again, we're in the third quadrant. We know sine is only positive in the first and second, so it has to be negative here. So we're going to have a negative root 2 over 2. And last one here, cosine of 5 pi over 3. So we're going to have to count. Okay, so we're going to take pi and divide it into thirds. So there's 1 pi over 3. And then 2 pi over 3. Pi turns out to be 3 pi over 3. We then have a 4 pi over 3 and a 5 pi over 3. Okay, so the reference angle for 5 pi over 3 is pi over 3. So what is the cosine of pi over 3? The cosine of pi over 3, we go back to our unit, or our first quadrant of the unit circle. Pi over 3 is 60 degrees. Cosine of 60 degrees is the x-coordinate, it's a half, so we know the cosine of pi over 3 is going to be a half. So what is cosine of 5 pi over 3? Well, remember, 5 pi over 3 is in the fourth quadrant, and we know cosine is positive in the fourth quadrant, so this would be, this would be, we're 1/3 down there, this should be 1/2. All right, last thing we need to look at here is just one simple identity, and we're going to get into more identities as we go through the semester, but a Pythagorean identity. Okay, and so we should hopefully all know the Pythagorean theorem, right? A squared plus b squared equals c squared. And so we know that if we have a circle of radius 1, it can be described as the equation x squared plus y squared is equal to 1. And if we take our unit circle relationships, we know that x is cosine, so I could replace this x squared with the cosine squared, and I know that y has to be the sine, so I could replace this as a sine squared. So this is our identity here. Cosine squared plus sine squared will always equal 1. Okay? It doesn't matter what the angle is, as long as it's the same angle in both expressions. Cosine squared plus sine squared will always equal 1. And just one example of how we could use this. Say we're given that the cosine of some angle is 5/13, and we know that angle is in the fourth quadrant. So we know the cosine is 5/13. Now, we could do the whole right triangle bit and the Pythagorean theorem and figure out the missing side, kind of like we did earlier. But we can also use this identity above us. So we know that cosine squared of theta plus sine squared theta has to equal 1. Now, I know cosine is 5/13, so that means 5/13 squared plus whatever sine squared is has to equal 1. 5/13 squared would be 25 over 169 plus sine squared. And 1, if I wrote it with a common denominator, would be 169 over 169. We solve that for sine. We get sine squared is equal to 169 minus 25 would be 144 over 169. And if we take the square root of that, again, when you take the square root of both sides of an equation, you get plus or minus the square root of 144 over 169, which those are nice numbers in this example. So plus or minus 12 over 13. Now, is it the plus or the minus? Well, this goes back to the quadrant. What do we know about sine in the fourth quadrant? We know it is negative. It's only positive in the first and the second. So what is the sine of theta if cosine is 5/13? We know the sine of theta is going to be a negative 12/13. And if we computed that using sort of that triangle strategy that we did before, we would end up with the same thing.